So now we're going to get into a whole new topic that we haven't talked about at all before. And this is where the excitement starts, I think. So cross-classified analysis, so we just go through the bullets here. That has two between-level cluster variables, subject and time. Cross-classified analysis, you know, in multi-level settings deal with clusters that are not nested, like neighborhoods and schools. They're cross-classed. In that setting, you usually have several observations in the cross. Here we have only one. One observation for a given subject at a given time point. But the idea of using cross-classified analysis for longitudinal data is an old one. You can read about it, for instance, in Hugh Parkes' multi-level analysis book. So what we do is we generalize the two-level model to a cross-classified model. So for a simple case of random intercept, we can write the two-level model as y for individual I and time point t equal to a level parameter and a random variation over subjects around that level parameter. And then you have the regression slope on, in this case, the within latent variable centered part of the variable, and you add then a residual. So this is within subject variation. You can think of it across time, and this is between subject variation, characterized by subscript I only, not I and t, like we have here. The cross-classified model adds this part. This part is new. It says alpha sub t. So it's a random effect, just like alpha sub I. But unlike alpha sub I, it varies across time, not subject. Like alpha sub I, it has a mean of 0. So you can imagine that, for instance, early time points can have a high positive alpha value. Late time points may have a high negative alpha value, which would then be helpful, right, for describing a trend that goes down. But the average is 0, which I sometimes forget. Now, why don't we do this model all the time then if it's more general? Well, you have to pay a price. The base algorithm is considerably more complex and very much slower, as you saw in those timing examples. Now, timings are also something that's not fundamental. There's a lot of intriguing possibilities to speed things up, which also will happen someday. So, here's an example of cross-classified analysis. I call it a quick way to spot a trend in a variable. Trend analysis is done in many different ways in time series analysis for n equals 1. You do differencing and the like on the data, but here we model it. So what you see here is a cluster variable, cluster specification that has subject and time. That's time since starting to try to quit, in this case. So two cluster variables that sit up in the names equal list. T interval is the same. Analysis type is now different, cross-classified, random. Estimator still base, processor still 2, B iteration still, in this case, 1000. And now we have within, between subject, and between time. So here we have, for simplicity, a fixed autoregressive relationship. And then we have a variance component for the intercept varying across subject and varying across time. So this is alpha sub I. It's actually the variance of alpha sub I, and this is the variance of alpha sub t on the previous slide. Once again, we ask for factors for urge, and you can make the factor estimation more or less precise. This has to do with how many draws, how many iterations you use for these unknowns. There's a longer story behind that, but I'm not going there right now. And then you can do a so-called time series plot, which I think is one of the more exciting plots in the new Mplus. Time series plots are used for the observed data that we looked at for each individual, but it can also be used to plot factor scores, particularly with cross-classified analysis. So on the x-axis is time. On the y-axis is this alpha sub t, which we refer to as between level 2a underscore urge, comma mean. You can choose the median also. B2A is 2A and 2B is Mplus lingo for the between level for time, whereas 2B is the between level for subject. So anyway, this is alpha sub t, the estimated alpha sub t quantities over time. And you see a trend, right? It's a trend that you can interpret. It has to do with smoking urge. So there's something that seems to go down and then level off, which looks kind of substantively interesting. And we may build on that insight. So now the runtime is 1 minute and 10 seconds, not bad at all. Much thanks to only random intercept, nothing else random. Now we can take this impression of trend, which is totally non-parametric. We have not imposed any shape on this trend. This is what we observe in the data. In data as much as the model filters it, but we have not specified a functional form for it. Now we can specify a functional form like a linear or a quadratic, both in a cross-classified analysis and in a two-level analysis. And when we do it in a two-level analysis, a few minutes from now, we're going to come back to growth modeling of the wide single-level form and recognize that again in this shape. So this is kind of fun. So don't get lost. So first of all, we impose linear quadratic trend in the cross-classified case. So just adding to the cross-classified analysis that we talked about. So we still have cluster equals subject and time QD, and we still have analysis type cross-classified random. Now we're going to define two time variables, time and time 2. This is the linear part, this is the quadratic part. Because the time QD variable is on such a high scale, I'm dividing it down by 100 to just make it more manageable. But that's not essential. But those are variables we're going to use in the model, and therefore we have to declare which level they vary across. And we're going to say that time 1, time and time 2 are going to vary on the time level, time QD, the between time level, which is down here, right? Between time, that's where those variables appear. Not for the between subject, but between time. And the way you say that in Mplus, you put the level in parentheses and then the variables. And then you can have another parenthesis for variables that vary across people instead, rather than across time. So here we specify a functional form for the urge by regressing it on those two time variables. And here's what it looks like. Here's when you make it linear, that is, you only use the time variable, not the time 2 variable. Here's when you use time and time 2. And you see that you have a tighter fit to this curve for the quadratic than for the linear, suggesting that you should go with the quadratic in this case. We haven't done growth modeling here. We have done we're looking at the shape of the urge development over time.